Hello everyone, welcome to Code Enzyme, and in this video I am going to discuss about vector databases, basically how retrieval and storage happens in vector databases and the work that has been done till now. So I have been working with vector databases for around 6 to 8 months, and yeah, it has not been much time, but I think I have some experience with it. I just wanted to share that knowledge with you in this video, and so that is what this video is about. I just wanted to give you the various techniques that are getting used while implementing the vector databases. So let's get started, and first we will start with the storage techniques. Okay, so for those who have never actually heard about vector databases, let's just quickly discuss what is a vector database. Now, a vector database is a database. It is not like your regular NoSQL or SQL database. Vector databases are databases which are used to store high dimensional vectors, which are mathematical representations of features or attributes. Each vector has a certain number of dimensions, which can range from tens to thousands depending on the complexity and granularity of the data. Okay, so now that you know a little bit about vector databases, you might ask what a vector is and how are these generated. So vectors is anything, like it can be represented by a matrix. It is just a mathematical function of some kind of attribute. Like let's say you have a string and you pass it through this mathematical function. It is generally called a transformer or an embedding function, and you get this matrix, right? Like that. So basically you have some raw data, you pass it through an embedding function, you get the vector. Okay, and you store these kinds of vectors in a vector database. The raw data can be anything. It can be an image, it can be a string, it can be an audio file, it can literally be anything. Okay, now this embedding function can be based on anything. It can be based on machine learning, it can be based on feature extraction. Depending on the use case, you will change your embedding function, and using that embedding function you will make your embeddings, which are used to represent specific kinds of data using a matrix. Right now, once you have prepared your vector database, it is very important for fast and accurate search and retrieval process. Right now, these vector databases can easily find the most similar vectors based on some kind of rule that we will decide while creating the collection. Vector databases can easily find the similar vectors based on the similarity and the distances between these vectors, right? And this is actually just the core functionality of a vector database. Now, these vector databases can actually store almost any kind of data. It can be images, string, and audio file, and so on, right? Now, as the data grows big, there can be a lot of performance and scalability issues, and for that, these vector databases, like currently what we have, they are able to handle billions of vectors and so on. So in this video we are going to discuss all the methods of storage and retrieval that are getting used in the current vector databases. Okay, let's start with the storage techniques first. Now, as the data will grow, it will become difficult to query and search from the database, right? So one common storage technique that vector databases use is called sharding. And sharding is basically all the data will not be stored in one single cluster. It will be stored in different clusters. Basically, if you have two shards, your data will be divided into two parts or partitions, you can say, and these two data will be stored separately in these two clusters or partitions, right? And how this helps, basically, when you divide the data into two parts, it becomes easier to query in it, right? So sharding can really help you if you have some way of dividing the data based on similarity. Let's say there are two clusters that are forming in your data, and you can easily split them, and if you have a lot of similar data in one shard, a lot of similar data in the second shard, and so on, it will become your query will be very accurate, right? So that is where sharding comes, and there are two popular methods of sharding. One is the hash based approach, and another is the range based approach. Hash based approach is generally, it is like you have a hash function, and let's say it returns an integer, right? And you pass in all your data in it, and if it returns 0, you put them in one cluster. If it returns a 1, you put them in another cluster, like that. So that is how the hashing works. And next is simply sharding. You assign a key to your data, and basically you just divide it into partitions. Let's say first 1000 of your data goes in first cluster, and the second 1000 to 2000 goes in the second cluster, based on just the key of the data, like that. So that is how sharding works. Let's see the next approach. So the next method is partitioning. Now partitioning is a technique which divides the vector database into smaller and manageable chunks, right? Now these partitions can be based on anything. It can be your geographic locations, it can be your date values, it can be anything. Basically these partitions can be anything. It can be your date values, it can be your geographic locations, it can be your color values, let's say red, yellow, green, and so on. Basically what you are trying to do is, after you have partitioned your data, let's say you want to query by only on the data that is in green color, or only on the data that was accumulated in the last month, then in such kind of queries partitioning really helps. So that is why partitioning of your data is also important if you are trying to do that kind of query in your vector database. So the next technique is caching. Now caching is a technique where we store the frequently accessed data in a fast accessible storage, that is generally your RAM, right? Basically you have two kinds of storages, that is, one is a RAM and one is your disk storage. So the data that is getting frequently accessed, you want to put them in RAM so that it can help you reduce your latency while querying. Now caching can help you greatly reduce your latency and improve the performance while retrieving your vectors, and it can be used in your vector database to speed up the process of data retrieval. Now one way that caching works is your LRU policy, that is the least recently used policy. That means whenever your cache is full and another request comes up and you want to put one more vector into your cache, which data should be removed? So you remove the one that was least recently used. That means that came at the very last time. Another policy that you can follow is called the least frequently used, where you remove the data that is least frequent. So you also maintain a frequency table, and the one that has the lowest frequency you simply remove them. So depending on the use case, you can follow any of these caching policies. Another way that caching can work is, let's say you have a lot of partitions, let's say based on location. Let's say you have a location, you have a separate partition for United States, you have a separate partition for India, like that. And for every partition you can define your cache size, and that way you can optimize your querying, right? So let's see the next one, that is replication. Okay, so let's talk about replication. Replication is basically you create multiple copies of all your vector data and store them in multiple nodes. This will obviously help you in load balancing, and single point failures will reduce, and basically the durability of your vector database will improve. Now replication can be of two types. One is called the leaderless replication type, where every node is allowed to read and write data. Basically it will avoid your single point failures. Basically you do not really distinguish between nodes, which one is the primary, which one is the secondary. You allow all of the nodes to be able to read and write data, and this will actually help you in avoiding the single point failures. And the next one is actually called the leader follower model. In this model we have one node which is called the leader, and the other nodes which will be called the follower. So in this case we only allow the leader to accept the write request, and it will push all the writes to the follower nodes, but it may actually introduce availability issues which might require some follower mechanism to handle the leader follower model. Now let's talk about the search part. So when I say search, I mean the nearest neighbor search, not like the keyword search or by filter by metadata and all. This is actually a problem where we want to find a point which are closest to a given point, and we want to find the n number of points which are closest to that point, right? Now the closeness is defined in terms of the dissimilarity between these points. The less similar the objects, the larger will be the function values. Let's say you have a paragraph. Let's say you have two paragraphs. One is talking about something like Delhi elections, and one is talking about some mathematical functions. So these two, when you plot the vectors in the 3D space or n-dimensional space, these two paragraphs will be far apart, right? And let's say you have n number of paragraphs. Some paragraphs are talking about elections, like news articles are talking about elections, and some blog article is talking about competitive programming. These blocks will be near to each other, and these blocks will be nearer to each other, and overall these will be far apart in the whole vector space, right? So we want to find, let's say you have a point in the space, you want to find the nearest of these two objects, right? Now vector search can be nearest neighbor search, or it can also be approximate nearest neighbor search. Now approximate nearest neighbor search, or ANNS, is a type of nearest neighbor search only, which allows some error of approximation in the search result, but in return you get some speed and space efficiency. Now ANNS, or approximate NNS, is definitely more useful for large data sets. Like let's say you want to find some products which are similar to a product, then you don't really need to get like accurately the products that are closer to a product. You can do some approximations where the actual accuracy does not really matter that much. That's where you can use ANNS, right? Okay, so first we are going to talk about the nearest neighbor search. Now obviously when you are going to find the nearest neighbor, one is the brute force way. Like you take a point, you find the distance of this point to all other points, and then you sort them, and then you will find your closest points, right? So that is your brute force way. So this algorithm basically guarantees that you will find the closest nearest points to a given point, right? So the time complexity will be basically big O of n time if you don't consider the sorting part, and the space complexity will be big O of 1 time. Now next is the tree based approach. Like if you don't want to go for a brute force approach with big O of n time, let's say you have a very large data set, you don't really want to go for a big O of n time, right? So the next is your tree based approach, where you can trade off your space and time complexity. In return you will have a faster querying time. What I have heard of, these 4 trees are getting used. One is the KD tree, one is the ball tree, R tree and M tree. Okay, so let's just quickly talk about all these trees one by one. KD tree is a way of organizing points in a k dimensional space, where usually k is a very large number, and it works by building binary trees where every node is a k dimensional point. Now that actually I am discussing it, I can go through each of these trees, but I don't think anyone is actually going to go and implement these themselves, right? So I think we can just skip on it. It is just good to know that there are actually 2 ways. One is the tree based approach, one is your brute force, and that's it. Let's go for the approximate neighbor search. Approximate neighbor search, we can actually divide it into various subcategories. One such category can be called hash based approach. Basically you create hashes of your search and you try to approximate things with that. And even in this hash based approach you can have various. One can be your local sensitive hashing. Now this is generally used in large data sets, where you generate hashes of a vector and try to form a compact binary tree using these hashes, and you simply try to retrieve these codes using a simple query function. Another technique can be your spectral hashing. This is also used in when you have a large vector database, and it works by using the spectral graph theory. Basically you try to create vector codes and you try to maximize the variance of these codes, and using that you try to minimize your errors and try to approximately query your vectors, like that, something like that. Next one in this category is called deep hashing. Obviously this is also used when you have a large collection of vectors. It works by using deep neural networks to create the hash function, and basically these hash functions will be used to transform your higher dimensional vectors into binary codes which are compact, and then based on similarity search you can query on these binary codes. Now obviously these hash functions must be designed to preserve the semantic information of the vectors, meaning that more similar vectors must be close to each other and the different vectors must be far apart. Now even deep hashing is divided into 2 parts. One deep hashing method is by minimizing the reconstruction cost whenever you put in a new point, and another is by minimizing the quantization errors. You can read about this by googling them yourself, or if you want dedicated video about it you can tell me in the comments. Now obviously the advantage of deep hashing is we can use our own neural networks to customize the hash function to improve its efficiency, and obviously the performance of these deep hash functions will depend on various factors like such as the architecture of the neural network and the loss function that was used to train the neural net. So the next is the tree based approach. So obviously even in ANNS we also have some tree based approaches that we can follow. So the first method is called the approximate neighbors. Oh yeah, I'm not sure who named it, but it is a technique where you build a lot of high dimensional trees and try to query into them. Now this works by building KD trees. You basically partition your data into bins, and then you search for the closest bin that has the query, and once you find the closest bin, this algorithm actually tries to find the closest points in that particular bin. The next method is called the k-means tree. Now this is a technique of transforming high dimensional data into a hierarchical structure where each node will represent a cluster of points. The performance of k-means tree will depend on several factors like the dimensionality of the data, the number of clusters per node, and the distance metric that was used while making the database. Okay, so that's it for the tree based approach. Now let's move on to the third part, that is the graph based approach. Now the first method that I'm going to discuss is called the navigable small world. So this is a technique where we use graph structures to retrieve the similar data points. So basically you have a graph node for every data point and you try to add edges and assign different weights to it so that you can query the closest points to a particular node. And the second method will be like very similar to this one. It is called the hierarchical navigable small world. So this is basically a state of art technique for finding the nearest neighbors of a vector given a large collection of vectors. So the difference is basically it uses a greedy search strategy to find the nearest neighbors instead of something like a DFS, and it basically builds a hierarchical structure like that and try to query the approximate neighbor. Now there are a couple of more methods like product quantization, online product quantization, and optimized product quantization, and that pretty much sums it up. So that kind of finishes up the video. Basically I just wanted to experiment how much of my audience actually is into this kind of content. So if you want me to go deeper into any of these topics, feel free to comment down and I will make a separate video dedicated to that particular topic. So yeah, thank you for watching and I will see you guys next time. Thank you.